Have you ever timed how long it takes for a chemical reaction to turn blue? Or measured how fast a radioactive nucleus decays? In chemistry, time is as essential as mass or volume, and our standard unit for it is the second. The second, symbol S, is the SI unit of time. Originally, it was defined as 1/86,400th of a mean solar day. That's the time Earth takes to rotate once on its axis. But since the Earth's rotation isn't perfectly consistent, scientists needed something more reliable. So in 1964, a second was redefined with extraordinary precision as the time taken for 9,192,631,770 vibrations of radiation emitted during the transition between two hyperfine levels of the cesium-133 atom. Yes, atomic timekeeping. That's how we measure time in labs, GPS systems, and even reaction mechanisms, ensuring global consistency down to the tiniest fraction of a second. Now, while a second is our base unit, in science, especially in fast paced processes, even a second can be too long. Think of flash photolysis or femtosecond spectroscopy, these need smaller slices of time. That's where submultiples of the second come in. A millisecond is 1,000th of a second. A microsecond is 1 millionth. A nanosecond, that's 1 billionth of a second. And even shorter still, in nuclear reactions, we sometimes use a quirky unit called the shake, which equals 10 to the power minus 8 seconds. These incredibly small durations are used when reactions happen faster than you can blink. So, whether you're watching molecular vibrations or triggering rapid chain reactions, these subunits let you measure it all with razor sharp precision. Let's now zoom out and build upwards from seconds into time units you use every day. A minute equals 60 seconds. An hour is 60 minutes or 3,600 seconds. A day has 24 hours, that's 86,400 seconds ticking by. What about a month? Well, that depends on the calendar, but on average, 1 month is about 30 days, which comes to approximately 2.592 times 10 raised to the power 6 seconds. These familiar time frames, minutes, hours, days, and months, aren't just for clocks and calendars. In chemistry, they're crucial for monitoring reaction durations, waiting times and titrations, and temperature control intervals. What about longer cycles, like a year? A year is defined as the time the Earth takes to complete one full revolution around the Sun, that's roughly 365 days or 3.1536 times 10 raised to the power 7 seconds. But here's the catch, the actual orbital time isn't exactly 365 days. It's around 365.2422 days. To account for that tiny fraction, we add one extra day every 4 years, that's your leap year. So a leap year has 366 days. However, there's a twist. Century years like 1900 and 2100 are not leap years unless they're divisible by 400, like the year 2000. This fine-tuning ensures that our calendars remain aligned with Earth's motion, which is critical not just for astronomy, but also for long-term chemical tracking, like radioactive decay or historical dating. Let's step even further into the vastness of time. A decade is 10 years, which equals about 3.1536 times 10 raised to the power 8 seconds. A century, or 100 years, is around 3.16 times 10 to the power 9 seconds. And a millennium? That's a whopping 3.16 times 10 to the power 10 seconds. These may seem abstract, but they're very real in chemical history. Think about fossil dating, carbon dating, or even the age of ancient artifacts. These massive time units help us connect chemistry to geology, biology, and archaeology. Whether it's tracking Earth's climate history or understanding the buildup of compounds in sediment layers, We need units that span centuries and beyond. To make sense of all these units, let's quickly convert them into a common language: seconds. 1 minute equals 60 seconds. 1 hour is 3600 seconds. A day is 86,400 seconds. 1 month clocks in at approximately 2.592 million seconds. A year gives us over 31 million seconds, and from there it scales to decades, centuries, and millennia. These conversions aren't just mathematical, they're essential for chemistry. Whether you're converting half-lives, balancing reaction durations, or programming time-sensitive instruments, knowing the second equivalent keeps your calculations accurate and meaningful. Time, though invisible, controls everything in chemistry, from the rate at which a reaction proceeds to the half-life of a radioactive isotope. Some processes unfold in microseconds, while others, like corrosion or radioactive decay, stretch over years and even centuries. The key is to use the right unit for the scale of the process. Imagine trying to express a femtosecond reaction in minutes. It would lose all significance. That's why the second, defined so precisely using cesium atom vibrations, is at the heart of all scientific timekeeping. So, whether you're studying how quickly hydrogen reacts with chlorine or calculating how long carbon 14 takes to degrade in a fossil, one thing is clear: in chemistry, every second counts. I hope this session helped you appreciate the deep role of time in chemical measurements. Up next, we'll explore how derived units are formed by combining fundamental units, like how force becomes mass into acceleration. Until then, keep your curiosity ticking.